Okay. Move this down a bit. So hello, everyone. Thank you all for coming to our technical interview workshop. I'm Felipe Rangel. I'm the lead of the Google Development Student Club here at the University of Miami. I'm also here with Kavya, if you care to also introduce yourself.
Hi, so I'm Kavya. I am a sophomore studying computer science, and I am the lead for outreach and for workshops like these. Just excited to run through this presentation with Felipe.
Perfect. Okay. And yes, we will be going, the first section of this presentation will be over data structures, kind of like a brief overview of what they are, and as well as some, instantiation access of these data structures, because especially for technical interviews, they're very important to know. Pretty much like, these are like the basic ones, and you have to really know them, know when to use them, how to use them, and for what problems. And so it's really important for us to know these, and that's why I wanted to really target them. Okay. So first we'll have Kavya go over arrays.
Okay, so our first data structure is arrays. And as you can see, we have a visual representation of what an array could look like here. So we've got 3 buckets, and in each bucket you can hold another data type. It could be a primitive data type like an int, or it could be an object like a string. And they're basically containers for data. Okay, so next we have a more mathematical representation of what an array could look like. And key features to note is that when you're indexing through an array, you start at 0 because computer scientists start counting at 0. And the length of the array, however, is in more natural numbers. Okay, so Felipe does not believe in cold calling, but I do. I'm very sorry, but this is arrays. Everybody here is, yeah, like it's the end of freshman year at the earliest for people. So does somebody want to tell me? And if nobody does, I will cold call instantiation for an array. And what this line of code does, what it means. Nobody? All right, so Carter, you mentioned that you're at the end of freshman year. Do you want to give it a go? Because I remember that or the first semester of freshman year, I remember that that was super array heavy, at least for me.
So it's going to create a new, basically a list of strings, and they'll all be set to null.
Perfect.
And there'll be 10 of them.
Mm-hmm.
Awesome. Okay, and then for access, we just, again, note that when we're trying to access any piece of data in the array, we start from 0 and we include it in the square brackets. For insertion and replacement, you cannot insert new elements to the end of the array because arrays are immutable, but you can modify existing pieces of data, and that would be replacement. And then again, for deletion, you cannot delete elements or change the length, but you can set items equal to null.
Okay, perfect. Now we'll go over linked lists. And so specifically in this case, we're going to be going over singly linked lists. There's also such a thing called doubly linked lists. So we'll just go over singly linked for the time being. So for single linked lists, basically what it is that you have what are called nodes, and these are basically like train cars. So that's kind of what the metaphor here is. You have right here what the head of the train car, and then these are just single links. So basically, once you go from the next to the to, let's say you're going from A to B, you can't go backwards pretty much. You can only go forwards. Whereas with a doubly linked list, you would have 2 pointers, basically a previous and a next, and so then you can go backwards and forwards. But we'll just go over singly linked for now. And so for here with instantiation, as you have probably seen in like your beginning computer science classes, you can have constructors. And so this is just basically a very simple way of just making a constructor for a node. And so for here, you have the data for the node, and you have the next pointer for that node. And so if we want to just construct this node, we give it some data. So in here it's int d, and then we do data equals d, and then next null. And so when we're instantiating these nodes, of course, we give it a name, and then we're going to set the next of this head node equal to another new node, pretty much. Now the main difference between linked lists and arrays, especially when it comes to Java with array lists and all that jazz, is that for accessing them, we have to follow this chain. We can't really just, go straight to a node. And so that's the main difference. And so in this case, to iterate through them, we basically have a temporary like cur node that we set equal to the head. And we have some, data to look for. So let's say it's number 10. And so basically while this cur is not equal to null, basically, well, we're not at the end because null is the end. We have to keep looking for this data. And if we reach that data, we break out of this loop and let's say we return true. Else we just keep moving through this chain. We keep saying here cur equals cur.next. We just keep moving through this chain. Now for insert, there's 3 different ways we can insert into this linked list. There is at the beginning of the linked list, the end of the linked list, and the middle of the linked list. It's all kind of the same thing. And so if anyone cares to maybe see in this little snippet of code, these 3 lines of code, do you think we're inserting in the middle, beginning, or end of this linked list? Just by looking at this. Okay. I don't want to cold call, but let's just pick someone random. Let's say Andres. Andres, do you think we're inserting at the beginning, middle, or end of this linked list?
Beginning.
At the beginning? Why so, you think?
Because you say head.
Oh, no.
Oh, wait. No, it's at the end because current is the last one, right?
Because node 3. Because we are technically it could be at the end. If like for example we only had like I said in this case 2 nodes, it could be at the end. But this also actually works for the middle. So if you were to let's say instantiate node to insert, make number 3, right? And then the next of the one we just made is going to equal head.next. So it's going to equal basically, let's say if you can see my cursor, we just made this. And it's going to basically equal now B. And in the next line of code, we're going to make head.next equal the one we just made. So basically we just inserted in the middle between these 2 nodes. And so that's the way you're supposed to like insert through these. And actually, when you think about it, to the longest insert, so like the one that's going to take the most amount of time is going to be at the very, very end, because first you have to iterate through the whole chain and then add towards the end pretty much. Because you don't have a pointer at the end, you only have a pointer at the beginning. So adding at the beginning is very easy, adding at the very end is very difficult. And then adding in the middle really depends. So that's for insert. For deletion, this is just deleting a node. So if let's say you want to get rid of C, we just make B equal to the next of it. So here's going to be B equals D. But remember though, we don't want to just get rid of the C and say, oh, it's gone. At least store it temporarily a little bit so then you can delete it, because otherwise you can have a memory leak and that can cause problems because this C will permeate through memory and it's never going to get deleted unless you really tell it to, at least make sure to do so. So that's kind of like a brief overview of linked list, the instantiation, access, insert, and we'll follow this kind of method throughout. But next we will go back to Kavya for stacks.
Okay, so to start off, this image is actually a poor representation of what a stack should look like, as Felipe pointed out to me yesterday. But I decided to keep it because I wanted to see if anybody else could think of offhand why this is not the most ideal image to represent what a stack could metaphorically look like. Does anybody know? Okay, Alfred, could you tell us why, if you can think of the answer, why this is not the best representation of what a stack looks like? Is he not there? All right. Who else here has completed sophomore year? Or like freshman year, I guess.
Can I try to answer it?
Yeah.
You go, Gail.
Is it because like stacks you can only like add to the top and like take out from the bottom. So technically here you can like add it to the middle.
Ooh, that's a good one.
That's a really good one. And another point that I didn't even think of as well. Felipe's original point was that you can only see the top element of a stack when you're peeking or like popping. You can't see all of the other like CDs and items. You only have visibility to the top of the stack. And in this case, you can see all of them. So therefore, now we have two reasons why this is not the best example of what a stack should look like. Does anybody have an idea of a better image or representation for a stack?
Maybe if they were in like a box that you could only look from the top.
Ooh, I like that. Like books in a box or something. That's
Mhm.
cool.
Like a cardboard box, like one where basically you
Yeah.
can't see through it. You can only see the top one.
Where it's opaque. And then Felipe's example from yesterday was the Grand Canyon, where you have many layers, but you can only see the top one and you can only access the top one and you have to like dig through the top layer in order to get to the second layer and so on and so forth. Cool. Okay, so stacks are a last in, first out data structure. And the two main functions, well, actually there's three. The third one's not on here, but there's push, which is adding to the end of the, no, adding to the end of the stack, right? Is it the top of the stack?
Top of the stack, top of the stack.
Thank you. Adding to the top of the stack. And then there's popping, which is from the bottom of the stack, yeah?
That's still the top.
Still top? Okay, this is not my day. And then of course there is peeking where you are just viewing the top of the stack.
Mhm.
Okay, so for instantiation, you can create a stack of any type, but I believe here we are using the object type of integer. And then for access, this is saying while we are looking for the number 10, and while it is not the data that we are currently on, and we are not at the end of the stack, continue to iterate and pop through. And then for insertion, we are here calling the push function, and we are adding 2 to the very top of the stack, and deletion is via popping.
Mhm.
Okay, so next we have queues, which are similar to stacks, but in other ways like an inverse. And here are two examples of queues. One is a Spotify queue, and the other is a traditional line of people.
Mhm.
Okay, so the two main functions for queues are enqueuing, and you'll add elements to the end of the queue, and then dequeuing, which is from the front. Queues are a first in, first out sort of data structure. So just as you'd imagine them to be with regular in-person queues. Okay, so for instantiation, we are declaring a queue of type integer here, and it is an interface, so we have to make it of a type linked list. And then for access, this is pretty much the same sort of access function as we had for stacks. So basically, while we haven't reached the number that we're looking for, and while we're not at the end of the list, and then insertion is offering instead of pushing, and then deletion is pulling instead of popping for queues.
And that's
Anything
pretty
else that you
much-
want to add before we go on to the next?
I think that's pretty good. Yeah, so basically for, I guess as a whole, it's very important to know about stacks and queues. I guess in terms of some other use cases, for stacks, if you ever wondered, kind of like if you're Control Z, your undo, that's basic when you think about a stack, because let's say you're working a Word document, you type everything out, right? And so whenever you Command Z, it pretty much undoes the last thing you just put, and so that's basically kind of like a use of a stack. In this case, it's just popping off the stack, right? And then for queues, it's kind of like your, your normal lunch line pretty much. And I guess in a real world case scenario with queues, it would kind of be like, for example, like Amazon orders, you would want to process the first order that comes in. So let's say like November 5th, you place something, process that first versus processing November 20th first, for example. There's probably some other stuff in there, maybe some like, oh, maybe it is like closer to the user as well. Maybe you want to process that first, but in the general grand scheme of things, you want to process the first thing that comes in, right? So that'll be your normal queue. And so now our next thing are trees. Now trees sometimes can be a bit scary, I'm not gonna lie. They're kind of like one of the weaker subjects, personally, subjects for technical interviews for me, but they are used as, of course, and you should definitely know about them. So here's, for example, the British royal family tree. But as we're gonna see, this tree is actually slightly different than some other trees we're gonna see. So here's you probably already know about this, the binary search tree. So the main characteristics about binary search trees are that there is only one root. So at the top, there's only one root, and each node, so each node in the tree can only have 2 children, no more than 2. And also everything from the left of that node is less than the value of that node. Everything to the right of that node is greater than the value of that node. So in this case, let's say we want to find the number 13. What we have to do is say, hey, is 13 greater than or less than 8? It's greater, so we go to the right. Is 13 greater than 10? Yes, we go to the right. Is 14 less than or greater than 13? So 14 is greater than 13, so we go to the left. Or 13 is less than 14, so we go to the left. So there, we find our 13. If we wanted to find 12, we would do that similar path, but actually it wouldn't actually be there. So there we would give our null pointer. Would say we didn't find it in the tree, basically. And so just comparing this tree and this tree, what are some differences between these two types of trees that you guys can see? Anyone can care to answer pretty much. Andres, you want to go with this one? Just like what are like at least some differences you see between the trees?
Can you repeat the question?
Okay, what are some differences you can see between this binary search tree and like let's say this like family tree pretty much? Like what are some differences you can see?
Is it the number of nodes it points to, branches?
The number of nodes you
Maybe.
said?
Like the number of branches it has.
Number of branches. Yes, I think you're going along that line. Like specific, let's say for example, this especially this generation line. How is it different from like this one, for example, the 3 and the 10?
Can you go to the last one? Oh yes, yes.
Yeah.
Oh yeah, it has more nodes than the last one. Is that?
Yeah. So pretty much in this case, you have what is this, 5 or 4 children, and yeah, so you have 4, or yeah, well, it was 3, technically 3 children, and 2 of them are married. And so you have 4 of these versus only 2 here. So that's the main thing with binary search trees. There's only 2 children, only 2, no more than that. And as well, in all technicality with a family tree, you need 2 parents. In this case, you only have 1 parent. So that's really some of the main differences. This would technically be 2 roots when it's only supposed to be 1 root pretty much. So binary search trees are used, and for sure in technical interviews, these will pop up. Some ones I could think about are like find the larger subtree in this binary search tree. So stuff like that do come up, and that's why you have to know how to use them. And also, especially it's recursive. I know sometimes when we hear the word recursion, we all freak out, but that's kind of like what it is. So you have this parent-child relationship. Leaf nodes are ones that don't have any children. So like these ones, 1, 4, 7, and 13 don't have children. And there's also a difference between depth and height. Depth is going down, height is going up. When we're traversing a tree, we can do it in 3 different orders. Here they are listed out, but it's basically just, are we going to do the left branch first? then the parent and the right, or do we do left, right, parent, or in this case, parent, left, right? So they're just different ways of just, order, going through them. And here's just, more of a formal definition of it. But yeah, just here in this case, we're just trying to insert a root, a new key into this. We just traverse through the tree and then find its correct place. Okay. So we got sets. So the sets are actually not too bad to understand. They're pretty easy to understand. And here's the metaphor of like, billiards balls pretty much. But pretty much sets are, there's only one data type, typically just one data type. There's no duplicates, and it's fast because it's hashed, and it's unordered. Does anyone know what it means for something to be hashed? Anyone care to explain? Cardi, you want to go with this one? I know you're just a freshman, but maybe you might know what hashed means.
So each item in the collection goes through a function that gives it its index to be stored at, I believe.
Yeah, you're on yeah, keep going.
And then, so in order to, you would be able to access it in instant time, because if you run the hash on what you want to look up, that would be the index, or generally.
Exactly. So that's kind of an implementation of like a hash bucket. So with like buckets, which I'll go into a little bit later. But yeah, pretty much like you find that index instantly. And so it makes it really fast. But Carter, what's the one thing you need for this set? Like if I give you a key, what's the one requirement for this set to even be able to be hashed then?
In order to hash it.
Like it's on the PowerPoint. It's like it's one of these 4 bullet points you're saying.
Oh, unordered. Yeah. Okay.
Not unordered, the other one.
Oh, I see what you're saying. You can't have duplicate.
Exactly.
keys.
So yes, it's great that sets don't have duplicates, because let's say, hey, find me, the unique letter throughout this, dictionary or something. And so it will just get just the letters and not any repeats, which is great, right? But you do have the thing where then like I can't check for any duplicates, and all that. So it is fast, but you won't be able to count those, but we are going to go into there a little bit later about how to do that. And unordered is unordered. So it is something you got to take to Intel when you add to a set. It's not going to be ordered, just like these billiards balls. They're all unordered, but at least they're all unique. So that's why sets are really useful for that stuff. And if you're probably going to take discrete math, and you're going to learn about set theory as well, which goes into all this. So in Java, it's pretty easy with sets. Instantiation, got your set class, or actually it's a set interface with the hash set, using a hash set. So with that, you already know it's hashed. To access it, you just say, hey, does it contain it? And when you usually use dot contains, let's say with a string, why don't you want to use dot contains with a string? Does anyone care to go? Let's say Guile. Why don't you want to use a dot contains with a string? What's the potential hazard with that? If you're a Guile.
Wait, can you repeat it?
Okay, so what would be the potential hazard of using dot contains on strings?
I have no idea. Maybe maybe spacing, or like I don't know.
Okay, but not the spacing in particular. It's more so like, think about it, like when you're gonna check to see if something is in a string, what are you gonna do with that string then? How are you gonna do that process? Like to see if it even contains it.
I actually don't know.
So what it typically may do is it starts at the beginning of the string and it goes until the end of the string to find whatever you're looking for, right? But
Right.
that could be horribly inefficient. So that's why this dot contains is not doing that. It's actually just hashing it and then going straight to it. So basically its time complexity is, which we're going to go into, is instant. Like it's going to happen constant 1. Whereas if you dot contains with a string, it could be n, It can be at the very end of the string, and then you just wasted a bunch of time pretty much.
Okay.
That's the, so that's kind of what it was. That's why always check to make sure your doc contains actually has a good time complexity, and don't like assume it's going to be O of 1 or something like that. So yeah,
Okay.
no problem. And so for insert for these sets, what you do is that you just add it. It's pretty simple. And then for remove, it's the same thing. What it's just going to hash the integer, and it's going to check it and add it. And if it wants to remove it, just hash it, go to wherever it is in the database, or if you're doing a hash table, you go to it and just delete it. Boom. So sets are pretty easy when it comes to doing this. And the next part we're going to be doing is maps. So maps are basically, you grab a set and you say, hey, I also want to give it the power to have it attached to something else as well. So, and just like with an actual map, I have all of the United States right here, and I have as well the capitals. So in this case, my set is all the states, which in this case, let's say strings, they're just names of these places. And we're mapping them to as well their capitals, which are as well strings pretty much, right? And so we're saying Florida, let's say Florida's capital is Tallahassee, Austin's capital, or Texas capital is Austin. And so what we're doing is just mapping it. So that's why it's literally called a map. So we have one data type to another data type. And this is extremely useful for a lot of different problems. And so there's out of really all these data structures, one I would really recommend knowing well are maps, to be honest. And like I said, it's just basically like a set to like some value pretty much. They are fast because they're you can do them in two different ways, hashed or tree. And with C++, it defaults to a tree. And for Python and Java, you have to decide that for yourself pretty much. I think in C++ you can also probably do it in a hash, but at least in the basic map, it's going to be a tree structure. And with a Python or Java, it's going to be, you can choose them. And so as I say here, there's advantages and disadvantages to choosing it. So for hash map, it is fast because it's hash, but you do get the disadvantage. It's a random order. Tree map, you get the advantage that it's ordered, but you also get the disadvantage that it's a tree in that it's not instant like a hash. You have to go through the classic, structure of like, hey, is it less than or greater than, right? So you have to do this whole thing. It's going to take more time than if it were a hash, okay? And then you have a linked hash where it's not random, it's not ordered, but it's actually depending on how you insert it, because it's basically doing a linked list. If I go all the way back, it's basically just adding it to this car, it's adding to this train car. So depending where it is depending how it's going to get ordered pretty much. So those are the three different types. There's actually, I think there's a little bit more as well in Python and Java, but for these are like the different types for them. And so it also depends on your programming language. If you're in a technical interview, maybe you want to use C++ more because you're more comfortable with that with trees, or maybe you want to use Python. It's all up to that, or depending on the problem itself. And so here you have an instantiations. You have a string, integer, and we got our map. And then we have our access. So here we're just using strings. So, bird, and that's going to return the value of that. So if that's already in there, it's going to return, I don't know, maybe 5 or something. There's 5 birds or something. And then for insert, we basically give it a string and the data, and we just put it into the map. We just use the dot put for this. And then for remove, you just give it the key and it's going to get rid of everything pretty much. So yeah, that's pretty much, so maps are very important, and I would really stress that as well, to knowing them. And here's just the implementation of these maps. And so I kind of give this metaphor of, or this analogy of like books in a library. If you ever say at the Richter Library you want to look at a book, this may be a way of how they actually do it. So they could use a map. So you give them someone give me the name of a book. Give me some name of a book. Anything, it could be anything. I don't care.
Harry Potter.
Okay, Harry Potter. So let's say Prisoner of Azkaban. So Prisoner of Azkaban, let's say you want to find it if it's available. And so let's say this would be a string, right? This would be our set would be strings of all these names of books, right? And so we then have to give this to the computer. The computer is going to compute for us some number, right? So there's going to be a string to integer map. And so then once you get the number, you can go to your, let's say your library, you can go all through there, say it's in the, I don't know, maybe it's 10 or something like that. And so you go to like aisle 10 for this book and you find it. So that's like the very primitive one. And here's just a more complex view of it. It's the exact same thing. You have your keys, which are named your books. And then that's going to map to a specific, this is basically like the computer. There's red and black lines, basically the computer hashing it. And it's going to then point to a bucket, and then boom, then you have your entries. Now, I want to ask you guys about this. Maybe I can ask, say, Andres this one. So what is happening here, you think, where it says John Smith and then Sandra D? What do you think is happening here? What do you think happened here? Why is this occurring, you think? Why in the same bucket?
It has the same hash value, so it's in the same location.
And so what is,
And
so what is it doing there?
do you have a linked list for that?
Yeah. So,
You have like a linked list for that. So it points to, it points to different name data.
And so I said that, hash tables have instant lookup time, but in reality, on average, it is instant, but in sometimes it could not be instant. And so, Andres, what do you think would be the worst case scenario in this case then? With the lookup time?
I think was it N? Sorry,
Yeah.
I don't really.
Why would it be
it was
N?
N, right?
Like, why would it be N? Like, theoretically, like, why? Like,
because it really depends on how long the linked list would be, so you will have like to keep searching for it.
And then why would that occur? Like, what would have to happen with the keys for that to happen, though?
For what? Sorry.
Like for there to be an ON time complexity for the access, what would have to happen with the buckets? Like what would have to happen with them, These slots, these buckets.
You just have to find a good hash value for each data that you insert.
Yeah, so it's along the lines of the hash value. So in worst case scenario, what could happen potentially, though this usually never really happens unless it's very rare, these keys can all map to the same hash code. And so what that means is that they're all going to go to the same bucket. And because we're using this linked list structure, it's just going to basically become a glorified linked list. And so that's when you can get the access of O of N, but there are some remedies. What do you think are some ways to mitigate that issue so that you don't have that O of N time complexity? You think, Andres?
When you calculate your hash value, you have to make sure it's not that you don't have a good formula when you calculate it. And so you avoid anagrams and stuff, so you don't have your same key in the same bucket.
Yes. Okay, that's one. That's changing up the formula could help out. And actually, there are ways to do this. So for example, one way to do it is that you go each character and you multiply it times a number and then add it to some sum. And then you modulo by the number of buckets. That's one way you can hash this, but it depends what you're multiplying by. If you're multiplying by a power of 2, that's a really bad idea because powers of 2, of binary are very, they get along pretty well. So that could cause a collision. Collision is when, 2 keys fight for the same bucket pretty much. So you typically don't want to multiply by powers of 2. The best ones are usually prime numbers, large prime numbers. You can look it up in like a prime table. Look for a good prime number. That's typically the best ones to multiply if you're going to do that way of hashing. And then just besides changing the formula, what's another thing you can do? Sorry to pick on you. I'll be sure to choose someone else for the next one. I just want to finish this up.
Oh, you're good. What was the question?
So besides changing the formula, what's one other thing you can do to try to stop some manipulation?
You can, I think when you fill it out, you can just increase the size of the hash table,
Exactly. Yeah. You
right?
can just give
Yeah.
more buckets, but of course the downside of that is that means more memory, because look, I have 255 buckets here, but only 4 of them are being used. Like that's, you got to always make sure that, that the number of buckets you have makes sense for your problem. If you're only going to have, let's say 5 keys here, reduce the number of buckets. At least that's what I recommend, because that's a lot of wasted space. At least, and this is the case with a hash table implementation. So yeah, so buckets, yes, change the number of buckets. And so there's like the 2 main things you can do: change the formula and change how many buckets you're working with. And in actuality, there's also another thing you can do. So I don't want to confuse the terms, but I think this is with closed hashing. So don't quote me on this, but pretty much like, because we're using a linked list, that's like type of like closed hashing, where basically the bucket points towards this and you just go to the linked list. Another way you can do this is that instead of using a linked list, you can just have Sandra D be here in position 153 and just basically continue that chain. And so whenever you go to John Smith, it's going to point here, 152, or Sandra D, and you just basically, we're just going to say, hey, Sandra D is here. We're going to say, hey, we're not John Smith. And then we finally found Sandra D there. And if it isn't there, that means it's just null. Like it doesn't exist. So yeah. Oh, we have a chat. Quadratic probing. What do you mean by that, Gail? What's quadratic probing? I don't know if I'm familiar with that term.
Is it like when we learned about like linear probing or like quadratic probing, when you like give like basically so that it stops collisions, so that it like goes through, if it does collide, it goes through like this equation, which is the quadratic probing, to give it like another index.
Ooh.
Yeah.
In my algorithms class, I actually didn't even like learn about that, but I guess I'll definitely look that up as well as to see. But that would make sense. Like if you have basically you want to reduce as many collisions as possible. So if you have some special way to do that as well, that by all means, yeah. Because if we want to reduce them so we don't have these linked lists or anything else that will slow down the process pretty much. But yeah, for sure. I guess quadratic probing is a way of doing that. And
yeah, I suppose it's like when you were talking about like the odd numbers, I guess someone created like an equation for it.
Perfect. Okay. Well, that's our well, now we're going to go on to the next one, but for sure, thank you, Gal. Be sure to look into that as well. So graphs. So for graphs, we don't really have a specific, there's no like general like guide on graphs. It's more so just like principles and traversal methods with graphs. Because there's just different ways you can, make a graph. Like for example, in this graph, I have here 1, which is the central one. And then I have all these other like, nodes, like, these are all just nodes pretty much, but these nodes can have so many different pointers. So honestly, there's no like specific like instantiation or access or stuff like that. Because honestly, it depends on the problem you're looking at. So we're going to go over 2 different ways of traversing these. So we're going to go over queue traversal, and then the other one's going to be stack traversal. So if you remember our queues and our stacks from before, we're going to be using them again to go through all these graphs. This will be the same graph. So let's choose Carter for this one. Carter, what do you see just by looking at this graph, including as well the colors on these? What do you see? And the numbers.
Well, each node is connected to at least one other node, but they like a node could have multiple parents, I guess. Parents wouldn't be the right word, but if you think of comparing it to a tree, it can be connected from multiple nodes.
And what do you notice about the colors and the numbers as well?
You can have duplicate numbers.
Okay. I see where you're going with this one. But more specifically, I guess, like if you were to compare this to, I guess, some form of nature, like some part of nature, where basically, like, let's say you start at 1, and what do you think is happening from 1? Like
maybe like a new generation.
Okay, good. Okay, and it's kind of like if this was a bigger map or graph, let's say I had more 3s and much more 4s, what do you think is happening pretty much?
Maybe it's increasing exponentially.
Yeah, so it's kind of going like, it's kind of like an onion, right? It's like going through layers. That's kind of how it is with if you're doing a queue traversal. Now, Carter, I ask you, what do you think could be the problem if you're using a queue and you're doing it through layers? And you said right now exponential. What do you think is the problem with that?
It
Potentially.
could take a very long time to find a certain node if it's
Mhm.
towards the end of the onion, I guess.
Yeah, that could be a problem, but as well, like, think about it. How big are these layers? You know?
Yeah, they're getting even bigger through each layer. So if you had a lot of layers, it would take a lot of storage.
Exactly. So the one thing of a queue traversal is that, yeah, it actually could be faster because you have a lot more of these like at once, you're collecting all of them at once versus, where we're going to see stacks, where we're basically going to do a little bit, pretty much. And so with the number 2 here, you say, okay, everything. And so the way we do this is with a queue. So with the queue structure, what we do here is that we push onto the queue 1, okay? And that's pretty much, that's where we start. Then we're gonna push onto the queue all of the other connections of 1. So we're gonna push on all these 2s onto the queue. And then we're gonna go and we're gonna see, hey, are any of these the appropriate one? And we're also gonna push on to the queue all of their connections as well. And then we're gonna check that. And we're gonna push onto the queue all of their connections as well. So you can see it can be very massive. But but basically we are doing it in a layered structure. It's kind of like if I get a pebble and I throw it in a lake, it's gonna ripple. So it's causing this ripple effect through this queue. And so we're basically pushing onto the queue and then we're just dequeuing it to check it. So that's kind of how the queue traversal is. Now we'll check the stack traversal. So here's the stack traversal. So I'll say Gal for this one. Gal, what do you see differently with this traversal method versus the queue traversal method?
Some like different numbers can have the same color.
Different numbers have the same color. Okay. What do you notice about the colors themselves though? Versus the other one?
There's more.
Okay. Why do you think there are more colors? And also, and what order are the colors?
Order of the colors. They're like random.
I would recommend going clockwise. Go clockwise. Do you maybe start seeing it?
No.
Okay, follow the numbers and follow the colors. That's what I would recommend.
Is this like a rainbow? Like I have no idea.
Okay, so let me just kind of walk you through this. So what's happening is we're starting at position 1, node 1, and we're basically going in a clockwise fashion. So basically we're saying, okay, we're at 1, we're going to push on to the stack all of these different connections, and we're going to pop off the stack. Okay, so we're popping off the stack. So let's say we pushed, I don't know, 13, all these numbers. But these are the numbers in which it's going to be printed, like in order. So we're going to pop off the stack 2. Then we're going to push on their connection 3. And we're going to pop, and then 3 doesn't have any more connections, right? So we have to pop off the stack 3, 2, and then we go to 4 because that's the next one in line. Let's say it's the next one in the stack. We push that connection 5, and we push their connection 6. And then we also have 7. So basically then we pop off until we go back to 1 pretty much. And so, yeah, how do you think this could be used? Why would you want to use this traversal method potentially?
I'm not sure. Because it honestly kind of looks messy. Because like I'm just looking at 7 right now and seeing how it goes back to 1. I guess there could be a use for that, but I'm not sure what.
At least a good thing with the stacks is that the stack is small because
Right.
basically the stack is as long as the path you're traversing pretty much. So when we're going to green, it's only 3 things. We're going through orange, it's only 4 things, starting from the beginning. 7, 2, 8, 2. So that's the one advantage of the stack. But it could be slower because what happens if when you're traversing to look for something and you go down the wrong path? You have to wait so long to get to like the next thing. Let's say we were looking for 11 or 13. 13 would be the last thing to be looked at because we're going in a clockwise fashion. So that's a bad thing with stack. Whereas here, it would have been seen immediately because it's one connection away, you know? So,
Wait, I'm actually a bit confused. Let's say you're like searching for 7.
mhm.
So you can go 2 ways to find 7.
2 ways to find 7. Yeah, potentially because you go this way, you know, go through 6 and then you can find 7. Or you could have found it afterwards because you're going to pop this off the stack
Right.
eventually. So you are going to push 7 twice, but actually the best thing to do is that you want to push something that's already on the stack. So you might want to have a separate data structure as well to monitor like what the heck is on the stack.
Mhm.
And then say, hey, is 7 on the stack, yes or no? And then you checked, hey, it's not, so push it. So, but if you just want to have like, you know, stack traversal, because also one other thing is, see how with queues, you're kind of going through like layers, right?
Mhm.
The stacks, what are you doing instead though?
It's not really layers. It feels like everything kind of has its own thing.
Path. That's kind
Yeah.
of like it's kind of its own path. So potentially maybe you just want to say, hey, boom, I just want to find one particular path for this. And so it actually records how you got there. This is more so like what is there, and it's more so like how I got there and is it there. So typically actually, and most times you actually do use the stack traversal more so because of the fact it's smaller, even though it could be less time efficient because, you know, your queue isn't as large, you know, your data structure isn't as large, but you do have the advantage that it's smaller and it could potentially actually be a little bit faster. It just honestly depends, you know, there's always worst case scenarios and all that. So I at least wanted to offer at least some sense of how to traverse these graphs, because these could come up in interviews, you know, look at this graph, how would you traverse it, all that. So you have 2 different data structures for it, stacks and queues. And there's also other stuff. You'll learn in discrete math, like Euclidean path and the Hamiltonian path, basically like, oh, can I go from 13? Can I go from, let's say this starting point 13 and traverse the whole graph and get back to 13? Without traversing it like more like a path more than once, you know. I think that's Euclidean. Hamiltonian is slightly different, but those all have their own different paths attached to them. And you'll see it in discrete math if you haven't taken it already.
Yeah, I got you.
Yeah. So now this is the stuff that we don't usually like saying, complexity, but this is something important to know about all these different data types and all that. But I do want to move on to our umpire method because we only have 10 minutes left. So umpire method is very, you know, useful technical interview strategy, and we are going to go over one problem. So basically, umpire method is basically stands for understand, match, plan, implement, review, and evaluate. And here's kind of the definitions for all these. Understand. So let's say you got some problem from your interviewer. And so now what's the very first logical thing to do is basically to ask the interview as many questions as possible. You know, I want to ask them test cases, edge cases, you want to fully grasp that problem. You really want to understand what you're working with here. Match. Match is you want to get the correct data structure for this problem, whether it be a stack, queue, map. You want to, you understand the problem. You're like, okay, it's a lunch line. I know I have to use a queue for this, or it's like a Spotify queue. I know I have to use this. So you match the data structure to it. This is probably the most important step because that also determines your time complexity, because you want good time complexity. Plan is also a very important step, because with plan, you're basically taking whatever data structure you chose and basically making a draft of whatever you're going to do. And you communicate, and through all these steps, you always communicate with the interview. You always tell them, hey, what's going on? What are you thinking about? Even if you were, let's say, for example, you solved the problem, but you didn't talk at all through the interview, it's still a bad look because you weren't really communicating with them. And really, it's important to do so. So always make sure you're talking, you know, always be talking pretty much through this process. Implement, it's actually one of the easier steps because they don't really want it. Sometimes they don't even like make you compile the code. It's just, at least write it in like a, good sense, with your ifs and your whiles and your fors. It should be one of the easier steps. Then you got review. Review is pretty much run the test, run the test, any edge case you can think of, make sure it's robust. And evaluate is tell the interviewer, hey, this is my time complexity, this is my space complexity. Funny enough, I didn't even know what space complexity was during the Amazon interview because I didn't even learn it in school. So, but for sure know it because they do ask about it. They ask about both. So, and that usually is dependent upon your decisions and match and plan. So knowing the umpire method, let's go through just a small example problem. Okay, so here's the problem, guys. So return the most common letter in a very long string. In this case, thousands of characters. So first things first, it's our understand. So does anyone care to, maybe ask some questions, during this understand stage? Like, what comes to mind when you think of this problem? If I were like the interviewer, for example.
Are uppercase and lowercase a considered the same letter or different letters?
Okay, that's a very valid question. Does anyone else have any other questions? Okay, this is the stage where you ask basic questions. You can do Andres or Gael. Just ask any questions. Like if you were like in an interview, what would you do with this?
I guess, can there be multiple letters? Like if there's the same amount of, let's say, A and like B, can we return both of those?
Oh, you're saying that they have like the same, like A and B occur the same amount of times, right?
Yeah.
Okay, that's a valid question to ask. What about you, Andres? You have a question that you could ask in the understand part?
No, not really.
One other thing, think about it like this. When I say a very long string, and I say characters, what's something else you also have to make sure about? Like, what about this string? You know what I mean? Anything in particular you want to ask about the string itself? Okay, well, one thing in particular I would ask about this is also making sure that they're all ASCII values because you never know if you're gonna get a random string of just random stuff, and you got to make sure you're able to parse through it correctly either way. So you got to make sure you're adding stuff appropriately to the string. So that's one thing I would say through that. And so let me just click the next one. So pretty much, yeah, are all the elements of string ASCII? Carter said, is it case sensitive? It could be uppercase, lowercase. Is capital A different from lowercase a? And also, really, is there any specific space and time requirements? And also, can you give me like an example to this case pretty much? So next one, match. So when you think of like most common letter, and then you think of string, from all the data structures we just went through, what do you think would be the best match for this problem? What do you guys think? Anyone can talk.
Probably maybe a map.
Okay, good. Why a map? Why do you think so, a map?
You could have the keys be all the letters and then their values be the amount of times that they occur.
Okay, good. How are you gonna make sure that you don't accidentally add something that isn't a letter?
I guess you would have, or you mean for like the hash, how would you know it wouldn't go to?
Like for example,
a
let's
letter?
say, I don't know, the brown fox. How do I make sure I don't add the spaces by
You
accident?
could adjust the string to, you could just remove all the non-letters before you go through the string.
Question, do you know the ASCII table? Do you know the ASCII table and all that? Like, how like you have like all the standard characters and all that. I think space is like number 32 or something. But what's the good thing about the ASCII table? Do you know about it?
Oh, every character is linked to a number.
Exactly. Yeah.
Is that so? You could, I guess, you could use the number only if it's a non-letter number, don't add it to the list.
Exactly. So in the ASCII table, what happens is that all lowercase letters are in like a chain. A through Z is its own like range. And so what you can say, and in Java knows this, C++ knows this. So what you can say is like, if the key is, or whatever the character is, if it's greater than or equal to A and less than or equal to Z, that means I'm only going to look at the range of A to Z and say lowercase. And I'm only going to add it to the map if it's that. And if it's that, then we're good. If it isn't, then ignore it, because you don't want to add spaces. You know, the problem doesn't say ampersand or punctuation, so we don't want to do that. We're just asking about letters. So yeah, we want to look at the ASCII table pretty much. Yeah, so let me just go to the next one. So yes, the map would be the best one, also because you said like it's hashed, so you know, instant lookup time, and we would just map to, you know, how many times it appears, right? So does someone care to explain, like, kind of like just like a brief draft of how we would, you know, think about the algorithm for this? And we are limited on time, so if anyone cares, like, share how you would kind of go through this. Maybe Andres, Kyle, Carter, one of you three.
Maybe I would start by splitting the string into an array and then looping through the array and adding it to the map. If it's like, if the key was one of the, where you said 0 to 32, if it was a letter number from the ASCII table, and then increase the value. So I guess you'd have to start them all at 0. Or if it hasn't been in, you could also do, if it's not in the map yet, set it to 1, otherwise increment it by 1.
Okay, good. So yes, you're basically on the right track. So basically you make the map, you make it, and then you don't have to really make it an array, because when you a string is basically an array, so you can actually just iterate through it, and you just iterate through it, you know, normal for loop. And then as you encounter as character, we check, hey, is it a letter? Good. And then, is this letter already here? Yes or no? So if it's already there, then we just add 1, right? It's because it's already there. If it's not there, we add it to the map, and its default is going to be 1, because we don't want to add, like, because what happens if a very long string doesn't have all 26 characters? It could just have A and then not have any B's or C's or D's or stuff like that. So we want to, you know, add them to the map as they're coming in. Okay, good. And then it kind of, I already have here last step, but pretty much then we go through the map and we try to find the largest value. And Gal did bring up a good point. What about if, you know, 2 letters have the same? So maybe we just want to return both. Maybe we return a list. That wasn't a problem, but that could be something you want to add on. Like, you want to return a list of these characters that have the same, or just 1. So now if implement, I don't want to really go through much for this, but it's pretty much just, you know, follow through with your plan and, you know, just do it pretty much. Review. For this one, I did the example string of the quick brown foxtrots over the lazy dog, because it has every single character in the English alphabet. And so in your algorithm, it should return the letter O, because here O appears 1, 2, 3, 4 times, and it's the most common letter. So does that return O? And also, very important, make sure that you check for empty strings or null strings, and that they don't break your program. Pretty much at the very top of your program, check, hey, if string is null, return false, like return something, you know, just return. Or if the string is empty, return, because you know that those are not valid, but make sure you cover those, because there's edge cases that have to be covered. Evaluate. So we are running low on time, but can anyone think of, like, what would be the time complexity of this solution? Just the time. Anyone can go.
O of n being the characters.
Okay, and that's because we only have 1 for loop to go through the string, right? Only 1 for loop, and that goes through all the characters. That's already n. And then we have another for loop to then go through the map. right? So that's maximum. I mean, just go with the biggest one. So in this case, n. Now, what do you guys think of the space complexity of this solution, though? What is the space complexity? And space complexity, just so you guys know, is basically how big your solution is in terms of like how much storage is being used. And you use typically like, 1, n, n squared. So basically n is like, I take in, however many characters, and then I'm actually squaring it. So I'm using like basically a square of the amount of stuff that's coming in. So in this case, how big is your data structure basically? In terms of 1 n squared, stuff like that.
Okay, wild guess. Maybe it's constant because you're just adding it to like a counter, right? So it shouldn't take that much space.
You're a lot, not the counter. Think about it like, what are you adding? Technically, what are you adding?
You're just adding like how many times you see that character, right?
But I'm talking more so about not the value, but the other. So you have key and value. So talking more about the key. What about the keys themselves, though?
Not sure.
What about you, Carter? What's special about the keys in this problem?
It's not dependent on n, so there's maximally going to be 26, no matter
Exactly.
what n is.
Exactly. So the good thing with our data structure we chose that because you can have what? Duplicates. You can't have duplicate keys. So as these characters are coming in, it's basically just adding it to the same thing. And so our time and space complexity is O of 1 because we have 26 characters. And so, yeah, only 26 letters in the English alphabet. And so boom, there we have our time complexity of n and our space complexity of 1. So that's a really good complexity. Typically, when it comes to these interviews, you want to shoot for O of n for time complexity, or n log n or log n. You want to shoot for those. If you reach an n squared, basically means like two for loops. A for loop within a for loop is no bueno. That's like a brute force approach. You don't want to. If it's the only thing you can do, give it to them, but it's just not the best thing because it's slow. And space complexity, I mean, n is fine, but don't try to make it too much. But really, space complexity, time complexity is the most important one of all of these, to be honest. I don't want to go through all this right now because we're running out of time. But even though I wasn't going to go through all this to begin with, but this is just some sorting algorithms. You're going to go over these in your classes. So you get your selection sort. Here's just some animations. You select the number you want to insert. Yeah, you insertion sort. You're inserting your number. Got your merge sort, and so out of these sorting algorithms, merge and quick sort are ones you're going to be most using, right? So with merge sort, you actually basically it's kind of like a divide and conquer. It's similar to quick sort, where basically you took your array, you broke it up into some pieces, and then basically you're just putting it back together with a less than or equal to. So in this case, I think it's going to right now go to 5. Right now it's merging both of these arrays, and so it's comparing to see which ones the values themselves. So this one's saying, okay, which one's smaller? 2. Okay, 7 or 4? 4, 7, and an 8, because that array has already been finished. Now it's going to combine these two arrays. So say, okay, 1, then 2. Then we got 3, and it's saying 4. Okay, and then okay, 5 is smaller than 7, so it's going to put 5. 6 is smaller than 7, so it's going to put 6. 7 and 8. That's basically, it's kind of like divide and conquer. But the disadvantage of merge sort is that basically you have to have all these temporary arrays. So it does use memory, it does use memory. Quick sort does not use any extra arrays, but it could be, they're about the same. They're about the same time complexity. But you do have to monitor it. But the algorithm itself could be a little bit more complex. Don't want to go into too much depth because you will learn this in your classes. But I just wanted to show this animation and all that. Tree sort, basically another sorting algorithm, but instead using a binary tree. As you can probably tell with binary trees, like because it has that left and right approach, that's how you can also sort through that. Here's your complexity. Typically, your main guide, don't use selection range sort. They're bad. They're n squared. The inserts n at best, but still they're not really used. merged and quick are your go-tos usually. And then you have some other sorting algorithms like binary search and sequential find. But yeah, so those are your basic sorting algorithms. And it's kind of more towards the end of the presentation. But here's just some other books, you know, the Cracking the Coding Interview, very popular book that really any coder should know about. And if you really want to learn about this stuff for technical interviews, it's pretty comprehensive. It's a really thick book. It's like around 400, 500 pages, I would say. But it's really comprehensive. It goes through all these data structures, and it basically gives you like example problems. It also goes a little bit into behavioral. We didn't really do this in this workshop, but behavior is also important. That's more so the talking aspect of everything, like talk about your experiences, STAR method. I don't know if you've heard about these stuff, but for sure, it's good. If you're really interested in software engineering internships, pick up that book. And then of course, websites, there's plenty. Here's just ones I know. LeetCode, for sure, for your technical interviews, you're probably gonna meet either medium or hard style problems, not really the easy ones. And then Pramp is really good for interviews. So basically you kind of partner up with people and you can like practice with each other. It's like your peers basically. CodePath, which is what I took over this summer as well, just to practice a bit. It's really good. And they basically taught this empire method. As you can see, I don't know if you saw, I don't want to go all the way back, but here, this is actually from CodePath. This umpire method is from them. It's a really excellent resource. And the courses are completely free. So you can sign up for them. They're typically like every semester. And I really recommend to you to take some of their courses. There's like different levels of beginner, intermediate, and advanced. And they're really great. They're free, completely free. So you might as well, try to just apply for them. Why not? They're good. Also Udemy for certifications, and also AWS because, it's really good to have like cloud practitioner certifications to know how the cloud works, like how to deploy, how to code and all that stuff. And actually I'm next summer, I'm going to definitely get my certification in that. And then LinkedIn Learning, it's free for us students. UMiami pays for this. So for sure use LinkedIn Learning. You can as well get certifications, learn more, learn your Python and your Java. And yeah, so those are some just resources for your studying, for your interviews and all that. And does anyone have like any further questions? Just want to open the floor to any questions regarding interviews, regarding like, any experiences I have or anything like that. Or just your general thoughts in this workshop pretty much. I'll stop the recording.